And this might look like a homemade explosive, but it's actually just a time shutdown control box I built over 3 weekends. This metal rod I'm holding is called a microshaft, and my parents have been manufacturing parts like this for more than 15 years. And these tiny precision rods used in all kinds of mechanical systems, from small motors to gearboxes, even watches and medical devices. Anywhere you need smooth rotation or precise motion in a tight space, chances are there's maybe a microshaft doing the job.
This right here is a parts machine for miniature shop. It removes burrs left from machining and gives parts a much smoother surface finish.
We load the microshaft and abrasive media into container. Once the machine starts, motors drives the machine, drives the hexagonal barrel to rotate. And since the 6-sided shape just causes the parts inside to tumble continuously, forcing them to collide and rub against abrasive. That's what removes the burrs and leaves the shaft a polished finish. The one major factor that really affects the polishing result is time. If the polishing goes on too long, the part can actually become undersized. For example, if a certain shaft needs 20 hours of polishing, and I start at 10 a.m. this morning, and I will have to come back at 6 a.m. the next day, and just to shut the machine off. Otherwise, I have to split it to 3 days because a normal workday is only 8 hours, and that just sounds too ridiculous, right? Actually, fixing this is not that hard. All you need is to install a timer-based power-off controller, and we don't have to wake up at 6 a.m. anymore. To make this work, all you really need is an air switch, a contactor, and a time relay. Now, time relays are pretty common in automation systems, but when I actually got one from internet, I found that it was not that intuitive to use. The interface was not very clear either, and I was worried our workers might push back because of the external curve. So I decided to go with an embedded system to design the controller, and keeping the interface way much more easier to use, simple and intuitive. Since I'm not an electronics major, I did not know how to design a proper PCB, so I decided to just put everything together on the prod board using what little I know about circuit and coding. And thanks for AI, by the way. So I started by placing a basic microcontroller system right in the center of the perf board. This is the brain of the entire control setup. I'm using an STM32 series MCU, which frankly is overkill for something as simple as a timer. But hey, why not? For display, I picked a large 4-digit 7-segment LED. The catch? It has 14 pins. Connecting all of that directly to the microcontroller would eat up a ton of GPIOs and make the code unnecessarily messy. So I went online and found this handy little chip, the CH455G, a 7-segment display driver, and with it I only need 2 wires from the MCU to control the display. Super efficient. But this chip also turned out to be the most time-consuming part of the build. Since I didn't know how to use PCB, every single connection had to be hand-soldered. That means carefully managing all the wiring, making sure there's no shorts, a real challenge for someone like me who's still pretty new to electronics. To make soldering the fly wires easier, I clamped the chip down with alligator clips. I didn't just soldering wires directly onto the pins, so I took a bit of extra time to wrap each wire around the pin before soldering. That gave me a much more secure mechanical connection. About 30 minutes later, I had what looked like a tiny multi-leg insect made of wires and solder and a microchip. Since I am using 2 LED displays, one for hours, minutes, and the other for seconds, I needed 2 CH455G driver chips that definitely need more work, and luckily I am mentally prepared for it. Next, I had to figure out how to place both chips logically on the perf board, and then the real grind is ran all those fly wires through the holes and solder them one by one. Believe it or not, this took a ton of time. Wires were so close together that after soldering each row, I had to go in with a multimeter and check for shorts between the lines. Once all the connections were done, I added pin headers to each chip so I could easily plug them into the display module later. And to avoid any accidental shorts from all those fly wires, I used a bit of hot glue to hold everything in place and insulate connections. And honestly, I've no idea how much solder wire I went through. At one point, I genuinely felt like I was being slowly poisoned by solder smoke. About 2 hours in this soldering marathon, I lost count of how many times I swore to myself, "That's it, never again. The next time I'm learning how to design a PCB, no matter how long it takes." Because hand wiring and point-to-point soldering on perf board, it's just so inefficient, painfully inefficient. I also broke out a few GPIO pins to use as inputs for external push buttons to detect when they are pressed. And finally, if you see me cleaning up with a brush, this is a sign, means this board is basically done. As you might notice, I actually built the prototype board ahead of time, just to make sure the whole setup would even work. It's a budget box I found online for under $4. Barely fits to my 2-control box, but hey, it works. At this point, all I need to do was mount the boards inside the case and wire them up to the external buttons. For power, AC comes in through a circuit breaker, then gets stepped down by an AC to DC converter module on the board, supposedly giving me a nice stable voltage for the MCU and display. Though, to be honestly, I haven't actually measured it, so let's say it's just probably stable enough. Once the code was flashed onto the microchip, it was time to test if everything worked as expected. Good news, the buttons responded perfectly. But the 7-segment display, well, since it's being refreshed in a loop via multiplexing, it flickers like crazy when recorded by a phone camera. To the human eye though, thanks to persistence of vision, it looks totally stable. With the time set, I hit start button and click, the contactor engaged. In theory, that's when the motor should start running. After the countdown finished, you can hear another kata, a satisfying little sound that told me the contactor had disconnected. Now I bring the control box over to where the original switch for the partial machine is. The installation is pretty straightforward. Just connect the live and the neutral wires through the air switch, and then AC/DC module provides a stable low voltage power supply for the control circuit. And finally, wiring the motor's 3-phase wires into the contactor. That's it, everything's ready to go. By the way, to keep the video simple, I skipped part where I drilled into concrete wall and installed expansion bolts. In the control box, the contactor stays closed when the timing system is off. So in this default mode, everything works same as before, and in this way, I don't have to worry about the workers not knowing how to use the new system right now. But once the timing system is turned on, the contactor immediately opens. From that point on, the machine can only be started and stopped through my system. based on the ready time you set.
If you are interested in this kind of video or you are looking to order microshafts in big quantity, please subscribe to my channel, and of course you can leave me comments below. And what's more, our factory is located in Ningbo, Zhejiang province, which is on China's eastern coast. It has the most developed port of China. And thank you once again for watching this video, and see you next time.